Hello again in my electrical engineering portal channel. In this section, we will learn about three-phase currents. This topic is very important because when you start designing your protection system, you need to understand in detail how the electrical network behaves when it is operating normally. Only then you can design a system that reacts quickly and decisively when things go wrong. So in this section, we will learn balanced and unbalanced load under both conditions, that is with fault condition and without fault condition. Then we will see the basic difference between TPN and TP system and how it affects our system if we don't care about this system. And then we will see types of harmonics. This is very important because in every electric system we have to take care about the harmonics, especially when we are talking about high voltage or medium voltage and what effect they can cause on our system. So by the end of the course you will understand how the current vectors behave under normal condition, under fault condition, and how the current vectors can be analyzed to obtain information to give us the clues of a fault that just took place. Let's look at the three-phase system. Here, if you see, we have a source, three-phase source. We have a three-phase load. You can see the red phase, yellow phase, and blue phase currents will go towards the load side. And we have also a neutral system that head backs to the neutral point of the source. So this is our typical three-phase system and we call it as TPN system. N is understands for the neutral system and P is for phase. So in short, the neutral is a point where all the other three phases, that is red, yellow and blue phase currents, come together. To study in detail, let's see the two conditions. The first one is the balanced loads. As you can see, in a balanced load, all the three phase currents are equal and separated by 120 degree. So the whole clock will be 360 degree and the angle between one phase to another phase is 120 degree. The magnitude, this line depends on the load. The currents will come together on the neutral side. Therefore, the red phase, yellow phase, and blue phase current vectors all merge together. We can see that all three phase current vectors cancel out and the sum of them is equal to 0. Therefore, in balanced system, three phase in a balanced three phase system, the neutral current always equals to 0. Now let's see our second condition, that is unbalanced load. You can see that the magnitude of the three phases are not equal, but they are still 120 degree apart from each other. Here, blue phase is smaller than the other two phases. And if we take the summation, you can see that in this case, that is in unbalanced load, there is always a neutral current that flows. Thus, the three phases don't cancel out and there is now a neutral current which flows back to the neutral point of the source. Thus, in short, in TPN system, the current on the neutral varies between 0 for a balanced three-phase system right up to the full phase current when only one phase is loaded. We therefore must make the neutral conductor the same physical size as the phase conductors. as it may carry the same current as them. Therefore, we have to consider the neutral conductors as live as it carries currents. If we now summate the red, yellow, blue and neutral currents, they will always balance out and equal to zero. But in our three-phase transmission line, we don't normally have a neutral. Let's see a scheme. Normally in our transmission line, we have only three phases. The currents now act in a balanced circular motion. The direction of the currents in each phase continuously changes depending on the magnitude of the loads imposed on each of the three phases. For the transmission system, all we are doing is taking power from the source and it's going towards the destination. And we don't need phase to neutral voltages. There is therefore no point paying for a neutral conductor and we have a TPN system. But customers requires a phase to neutral voltage on the distribution side and a neutral is therefore required. To solve this problem, we have a TP system. In a transmission system with no neutral, the current phasor diagram looks like this. The currents will come together on the neutral side. Therefore, the red phase, yellow phase, and blue phase currents, all the vectors will merge together. So, the three-phase currents may vary in magnitude and change in direction, but the summation of all the vectors will always be zero, even in TP system, same as we studied in TPN system. We can also break down the three-phase vectors in terms of positive sequence, negative sequence, and zero sequence components. These three components vary in magnitude and angle, depending on how the system is behaving. Let's now change the system parameters and see how the components vary. So, as we discussed, there are three types of sequence vectors. The first one is the positive sequence. These vectors spin in an anti-clockwise direction from red to blue, blue to yellow. Then we have a negative sequence and here we can see it's in the clockwise direction from red to yellow, yellow to blue. And finally we have zero sequence vectors. These vectors have magnitude but no spin. Let's now vary the system parameters and see how these three components vary. First, we have a balanced load with no fault condition. In a balanced, healthy system where all three currents have the same magnitude and there is no fault, the positive sequence vectors that are created by the generator appear with the load. There is no negative sequence vectors and there is also no zero sequence vectors. Next we have unbalanced loads with no fault condition. In an unbalanced healthy system where the three-phase currents have different magnitudes and there are no ground faults, the generator still supplies only positive sequence vectors. The supply at the load now also contains negative sequence vectors which makes the balance supply. There is still no zero sequence currents. So let's look at this phasor diagram. As I told you, this is an unbalanced load but with a ground fault condition. What happened in this case? In this case, again, the generator still supplies only positive sequence that supply the load. The supply at the load now also contains negative sequence vectors. The supply at the load also contains zero sequence vectors. And this is our unbalanced load with ground faults. And this is a typical system. Maybe you are thinking why we are bothering all these things like balance, unbalance, and all these things. Well, we can use the information from the three components to analyze how the system is functioning. Digital relays use numerical analysis to obtain the three separate components in real-time data, and the zero sequence components are particularly useful. And these analysis gives rise to the study of harmonic analysis. The typical waveform of harmonics you can see time versus voltage, positive and negative value. Another feature of an alternating current system is the ability to use harmonic analysis to break down the sine wave into smaller sine waves components that have a higher frequency. A sine wave with 3 times the original frequency, for example 50 multiplied by 3 is equal to 150 Hz, will be classified as a third harmonics. Similarly, 5 times higher, for example 50 multiplied by 5 is equal to 250 Hz, would be classified as a fifth harmonics. And similarly, we have the seventh harmonics. Some equipments on the system can cause harmful harmonics that can reduce the lifespan of the primary plant, such as transformers. Typical equipment that causes harmful harmonics includes fluorescent lighting, capacitor banks, inverters, and some motor drives. In my other lectures, I will show how we can get rid of harmonics from the motor drives or the inverters in some separate lectures. We can use real-time analysis to identify certain harmonics in the system to support or block protection systems. So first comes our second harmonics. You can see higher level of the second harmonic can occur when a transformer is energized, causing large amounts of current to flow into it, causing an effect called magnetic inrush. This can cause maloperation of the main protection relays. Some transformer protection relays use second harmonic blocking to inhibit the main protection until the transformer is fully magnetized and the magnetic inrush subsides. Then comes our third harmonics, time versus voltage. High level of the third harmonic can create hazardous oscillations in the three-phase network and create higher than normal current flowing back through neutral wires. Then our fifth harmonics. High level of fifth harmonics can cause overheating in motors as they can push against the motor's natural rotation. As I told you, we will see these type of harmonics in our practical examples. In a three-phase TPN system, the neutral current varies from zero in a balanced load right up to the full phase current when only one phase is loaded. If we summate the three-phase currents in a TP three-phase system, we can get zero. We can split any three-phase current into numerous harmonics which have a higher frequency than the principal current. We can split any three-phase current into three subcomponents: positive sequence current, negative sequence current, and zero sequence current. So I hope you understand some of the key features of three-phase system, why we use harmonic analysis, what happen during balanced loads and unbalanced load and ground faults. So in the next lectures, I will go in detail with step-by-step detail. So keep in touch with me and like and subscribe my channel. Thank you.